Welcome everyone. Today is our last part in the StudyJam series. We started like series. I'd like to welcome you everyone. We are happy that you are joining us today at like the fourth session of machine learning StudyJam series. We are GDG Cloud Edmonton. We are an official chapter of Google Worldwide Network and Cloud developers, data scientists, and engineer. We are led by Vania. She's one of our speakers today, and our VP is Rohan Saha for this year. And my name is Shaima. I am part of the organizer team, and I will host this session of Machine Learning StudyJam for today's session. And we will also have our leader, Vania, will instruct the foundation of time series, trend, seasonality, and stationarity. With Devapriya will teach about modern approaches for forecasting, and I will be your host for this event. So please, if you have any question, drop it in the chat, and I will be happy to reply while presenting. Okay. So our group started like just before COVID, and we are now 747 members in Bevy, our platform. This platform we are joining from, and we are 1,400 plus followers in LinkedIn. We organized a lot of events like boot camps, Python, machine learning, study jams, and a lot of other events like the fests and many other things like women tech makers also hosted International Women Day celebration last year and this year. So maybe you met us before in person, or you attended some of our events online. We were doing all the events virtual since COVID started, and then we started slowly to do in-person events again. So this year we have in-person event coming is IO extended at Alta ML, Vania, I'm correct? Or University of Alberta?
Is the TELUS International Center at the University of Alberta.
Okay, perfect. And there
yes,
was collaboration.
University area.
Yes, so stay tuned for this event as well. It will be in person. If you are in Edmonton, we welcome you to join us. So first, we acknowledge that we are one of the traditional territories in Alberta of many First Nations, Métis, and Inuit whose footsteps have been marked as like this land for centuries. First, I will introduce you about maybe like Edmonton, where we are in Canada. So Edmonton is like the Prairie provinces in Canada, like beside British Columbia, and Edmonton, this is a capital of Alberta, if you are joining from outside. We have some code of conduct, like housekeeping we need to discuss, just be respectful for each other, like collaborate in good manner, and if you have any question, please ask and leave some space for others to ask as well. So for agenda for today, we will start discussing about two topics. So Vania will lead the conversation about the trend as seasonality with time series, and then Devapriya will talk about the models that the modern models that used for forecasting with machine learning. So I'd like to introduce for you like Vania. She will start the first session for now. You can take over, Vania.
Sounds good. Thanks, Shaima, for the introduction. I'm just waiting to share my screen.
Okay.
Hello, everyone. Thanks for joining us today at this Machine Learning StudyJam time series session. We hope you can enjoy it with us. Before to start, I just want to make clear that this is the Kaggle version of time series. It's not the typical time series concepts and notions that you're going to find in the classical time series literature, like the practical time series analysis by Eileen Nielsen or the forecasting principles and practice of Robert J. Hinman. Those are the foundations of the statistical approach of time series. This is different. It's like a Kaggle version. but I'm going to try to blend a little bit. Second, we are not going to cover the tutorial notebooks because I'm trying to save time so the Vipriya can expand better on more advanced forecasting techniques. But I prepared these slides. Sorry, that's a noise. Thank you. Yeah, I'm prepared these special slides and make this session a little bit interactive. Okay, we are going to start now. What are time series? A time series is a set of numerical observations on a variable of interest. For example, the demand of a service and price of gasoline. It can be also the signal that we can get from a sensor in the Internet of Things matter at the regular intervals of time. It can be on a daily, weekly, monthly basis, you name it. And these are techniques based on time series are quantitative models that predict future values based on the assumption that these values are dependent of past values. We can see in this this is a typical time series data frame. We can have the date and the hardcover sales of 139 for April 1st of 2000. Every data point is recorded at a timestamp. How the data processing works here? You need to use your date or timestamp column as your datetime index, and this can be achieved by using the datset underscore index or directly to the PD that read CSV and setting your index column as a date and parsing your date so automatically will convert your date column into datetime index. The typical index type for time series is the datetime index that I have worked on previous projects and the period index that Kaggle is using for their own tutorials. Before to start, we are going to make a quick recap about linear regression, also called ordinary least squares regression, which predicts continuous variables by using a single multiple linear regression formula. The input variables must be continuous as well. And the weight tells us how much the target changes on average for each unit change in the feature. In time series terms, the Kaggle approach is about like target equals weight by time step or time dummy plus a bias or the intercept. In Kaggle, they apply the linear regression, transforming the independent variable, converting it into time dummies in the ordinal type. So it starts with the index 1, index 2, index 3, and so on. And this can be achieved by the NumPy that error range with the length of the number of observations that we have on a data frame, or using deterministic process and setting these different types of parameters like to calculating the intercept. Mostly on the Kaggle exercises, we use false because we calculate the intercept directly at when we instantiate linear regression. Also, the order in this case, because it's linear regression, is order 1, but for series that they have like quadratic or cubic order, we translate it to 2, 3 as it goes. To the target variable, we don't do any feature engineering, and then we apply the model, instantiating the linear regression, and then fitting the data. Then, sorry, and then we start. We obtain our predictions, like show here. Okay, and now we are going to jump to the exercise. We're going to the Kaggle website. So we go Kaggle. This is it, right? And we go to this section, Learn. There's a bunch of courses. They are here on Kaggle, and for today we are going to cover time series. We'll go directly to the exercise. Now we are going to run this cell code to setting everything up, and I'm going to explain what it does, this part. Well, here they import the libraries necessary for the time series analysis, and then here they extract the data sets that we are going to work on this exercise, and they do like how we see here, they indicate that the date column will be the index column for this data frame, and it will convert directly to a date time. But at some point in this code, they do this arrangement of to convert the data type into period, because they use different like charts or visualization tools that they need the period index data type. Now they are asking us to run this cell. We see that here in Seaborn, they run us a linear regression, and they are just showing us how every data point of the hardcover cells, they are distant from the linear regression here. And now they are asking us to interpret linear regression with the time dummy. It says, the linear regression line has an equation of approximately hardcover equals 3.33 by time step or time dummy, plus the intercept of 150.5. Over 6 days, how much on average would you expect hardcover sales to change? Let's see how it works here. So they're asking us how much is going to change over 6 days. We only need to substitute the value. It changed by 19.98 the target. And let's see if we got it right. A change of 6 steps in time corresponds to an average change of 6 by 3.33 equals 19.98 in hardcover sales. Now I'm going to go back to the slides. Lagging. What is lagging about? Is simply sliding forward our previous values into one step further, or known as a forward filling. And we can do it through the dash shift, pandas dash shift method. And we indicate in the round brackets how many steps we want to go further. As we see in this table, we use the observation of April 1st for April 2nd. April 1st has not a lag value because it doesn't have a previous observation in March 31st. So this will be an automatically NaN. And later we are going to indicate how are we going to deal with this when we are instantiating modeling. Yeah, linear regression with lag values is like target equals the weight by the lag plus the error. The weight tells the dependence of the target with the previous step. So basically the weight, it tells us how much correlated is the lag with the current value. So it's a different term like in the previous linear regression. Also, lag 1 is not a dummy, sorry. It's just the numeric value. And the error is just random noise. Applying linear regression to time series for this, we need only to slide one step further our observations with the shift method one step ahead. Then add lag 1 in the data frame and drop the missing values. So basically we are going to drop this observation to avoid problems running our model. Then we need to match the length of our target variable y with the independent variable x with the align and making an inner join. Then we apply linear regression, feeding the data, and then we are obtaining our predictions and check, we are going to check how much correlated are the lag values and checking the intercept for a better explainability of our models. So we are going to back to our exercise. One moment. Now we'll get started with the store sales stamp series forecasting competition data. The entire data set comprises almost 1,800 series recording store sales across a variety of product families from 2013 in 2017. For this lesson, we'll just work with a single series average sales of the average sales each day. Now they're asking us to complete the code below to create a linear regression model with a time step feature on the series of average product sales. The target is in column called sales. Here, they convert the average sales into a frame, which used to be a series. And then we are going to create the dummies with NumPy, right? So it should be NumPy A range, the length of the observations, sorry. And then it should be DF index. Oh. Sorry, I'm just trying to check something. Sorry about this, guys. It's number 2, sorry. Run the following one cell to see 2 types of series. Here we see 2 kinds of series. And then it says one of these time series has the equation target equals 0.95 by the lag 1 plus error. And then the other equation target equals minus 0.95 by lag 1 error. What do you think each type of equation corresponds to these charts? Can you tell us on the chat? Can anyone infer which one correspond 0.95 by lag 1 plus error, and what is the negative minus 0.95? Don't be shy. It's okay to to get it wrong. Nothing happens. We are just learning here. Okay, probably today you are a little bit shy. I will give you a hint. It's just like one equation takes data points as they are. They don't change any direction, any signal. And the other one makes the series an intermittent behavior, like up and down, up and down, up and down. So can anyone can guess? Yes, Richard, you got it right. Yay! Good job. Let's see. Yes, as Richard infer, or the intuition of Richard was like series 1 was generated by the target 0.95 by the lag value plus error, and the series 2, it had a negative weight by lag 1 plus error. As I say, the series, the equation 0.95, it takes each data point without changing at all. It's just take it as it. But in the other hand, series, the equation for minus 0.95 by lag, it changed the signal of the data point, and this becomes like an intermittent behavior of up and down, up and down, up and down, as we see. And yeah, good job, Richard, and good job, everyone who got it right. And if you didn't, that's okay. Anything happened. Okay, we are going to go to the exercise that I was starting. So we are creating the again, I'm going to read the exercise. Is complete a code below to create a linear regression model with a time step feature on the series of the average product sales. The target is in a column called sales. Okay, here they convert the average sales series into a data frame. And then here we are going to create the time dummies with the length of the observations of this data frame. Now we have this new dummies annexed to this data frame, and we are going to select our features. So for X, we're going to have df log. We're going to take all the observations, and because when we are feeding our data, we need a 2D array. That's why we are introducing a data frame of the time dummies. Now, for the target, we only need a series type. So we are using log here, all the observations, and just is 1D array here, sales. Here we are instantiating our model. Here we are feeding. It doesn't indent. Okay. We are feeding, and then we are going to obtain our predictions here. We got it right. Yeah, okay. And then they are asking us to roll this cell, how this linear regression looks like. Here we have the model and each data point, how far are from this trend. Now, let's see how the coefficients looks like. We're going to obtain the coefficient for this model. I'm doing here a copy and paste, sorry, just to save time here. Let's see what is the coefficient for this model. The coefficient for every time step is 0.1943. And then what is the intercept of this model? The intercept is 194.23. That is, we can perceive it here in this part of the graph of the chart. Then how our model is going to look like. Yeah, our model looks with a weight. The sales are going to be affected by 0.1943 by the time step or time dummy plus the intercept of 194.23 as we saw in this graph. Now we are going to feed a lag feature to store sales. Complete the code below to create a linear regression model with a lag feature on the series of the average product sales. The target is in a column of DF data frame called sales. So for lag 1, we are going to use the shift method. And we are going to slide up one time step. Here, they are adding the lag 1 to the data frame. And also we are here selecting our X with the lag values and dropping the missing values, selecting our target. Here they are matching the length of the target with the independent variable X. And here we are going to run our linear regression. And then we are going to fit our data. Now we're going to obtain our predictions PD series. Then we are going to use model that predict X. And then we are going to use the same index from the independent variable X. And we are going to run this. Let's see. We got it right. Yeah. And then we are going to run the cell to see how this linear regression looks like with lag values, how much correlated they are. A simple side, we see a strong correlation here, but the question is how much are correlated? And again, I'm going to to do a copy paste to see in numbers the correlation of the lag values with the current data points. The correlation is a strong of 0.76. And we are going to just, because we want to check how much are distant the lag values with the error. Is 84.22. And how the linear regression for lag values looks like in the model. Sorry, I need to change this to Markdown. We have here the model for our reverse values of lag sales of 0.765 correlation by the lag values plus the error of 84. And this was the exercise for linear regression with time series. Now we are going back to the slides. We're going to talk about lagging. As I said, well, just to finish with lagging. Lagging is a simple but very used forecasting technique. We have here how lag values can tell us how future values can be based on 3 months or 6 months before. And also another example I want to show you is from the U.S. Energy Information Administration. They have these charts of the gasoline prices on a weekly basis. Just let me try to zoom in a little bit so you can appreciate it a little bit better. Here you have this chart. They have the original series here, but they also use a 8-week moving average. They are simply sliding up 8 weeks in advance, and they are also calculating the moving average directly here. Moving average is a concept we are going to see very shortly now. And then how it changes from 12. You see the gap. This is like they are using 12 weeks previous values to make a forecast, and they are also calculating the moving average. So it's an example that I want to show you how this is translating to the real world. Now we are going back to the slides. We are going to talk about trend. A trend in a time series is a systematic increase or decrease in the average of the series over time, where a significant trend is present. So for this graph, we can see from the motorcycle stock in the Netherlands, it has an upward or growing trend of a stock in thousands over the decades. Marathon times are reducing over the years, which is a decreasing trend or downward trend. Also, the Australian cement production has a growing trend by a quarterly basis, and we see here in the changes in the Earth's rotations, how it changed on years by year, and it has like an up and down trend. And this is not an uncommon time series. You're going to find it in many types of data, but are most common the ones that we have, which has the increasing or decreasing trends. Sorry. Okay, how can we calculate moving average? To calculate moving average, we use the rolling method to begin a window computation. A window computation, it consists on a specific time period. It can be yearly, it can be monthly, it can be, you name it. Later on the chat, I'm going to share where you can find the prefixes to set your specific windows. Here we have a rolling. We said there is a year window of 365 days. We want to calculate the average at the center of the window. the minimal periods, that is the half of the window size, and the start of the party, the mean function, because otherwise what is going to calculate, right? And in Christian terms, or in English, please, is how we calculate moving average, basically. For April, it's going to have the first moving average value because it uses the window from January to March. The moving average for May, it uses the window from February to April, and so on. So I leave this for a future reference. And for data processing, we use deterministic process to create the time dummies. And for selecting our independent variable, we use the ensample from the deterministic process. Then select our target, instantiate the linear regression. We are going to obtain our predictions. And for the forecast, we are going to use the attribute from a deterministic process and indicate how many steps I want my forecast after the last observation. And now we are going to jump to the next exercise. So we are going to go to our exercise. Now we are running this cell to set everything up. Let's see when it's ready, and then we are going to run this. Determine trend with a moving average plot. They use retail sales data set contains monthly sales data for a number of retail industries in the US. Let's see how this sales looks like in this chart. As a simple side, we see that food and beverage in the US has a growing trend or increasing trend over every 5 years. And we need to make a moving average plot to estimate the trends of this series. So we calculate to the rolling as we saw in the slides. How much is going to be our windows of 12 months because the data is recorded monthly. Then we're going to put an average on the center of this window. And the minimal periods, half of the window, as we say. And then the start of the party is the mean. Just to calculate the mean, the moving average. We got it right. So this is how the moving average trend here and how the data points are distant from their trend as we saw in the US gasoline prices in these charts. Is how they calculate the moving average here. It's not that different, sorry, from this the food and beverage sales. Now we need to identify what kind of trend this is this chart. What order polynomial trend might be appropriate for the food and beverage sales series? Can you think of a non-polynomial curve that might work even better? Before to think about it, I just want to show you something. What kind of trend are we seeing here? we are seeing different orders of trends. We see the linear one, that's linear regression, the quadratic function, the cubic function, and all above one linear polynomial. Can you identify which trend matches or it fits with these food and beverage sales? Can you say? Can you tell me in the chat? That's a great job, Erdi or Erdai. Yes, you got it right. It's supposedly is quadratic, but I also can tell you that it's not going to be the end of the world if you use order one, because the slope of this curve is not that pronounced. If you run it as a linear, it's not going to be a big deal. But here in Kaggle, they say we need to use the quadratic one. And let's see how we got it. That's right, the upwards bends a little bit and suggests a second order or quadratic. It says if you work with economic data times before, you might guess that the growth rate in food beverage sales is best expressed as percentage change. Percent change can often be modeled using an exponential curve. It says, don't worry if this isn't familiar. Actually, I'm just going to tell you that exponential smoothing is a very common forecasting technique to detrend your series. And soon we are going to cover about trending. We'll continue using time series of average sales in this lesson. Run this cell to see the moving average plot of average sales estimating the trend. As we see a little bit bend here for the average and sales in this lesson. And now they're asking us the following. Use the deterministic process to create a feature for a cubic trend model. Also create features for a 90-day forecast. Okay, for deterministic process. We are going to use the average data set. Then constant false, because as I said, we are going to calculate it directly at when instantiating linear regression. Order, because they are asking us a cubic, we are going to set order 3. Then we are dropping any collinearity. What does it mean here? As you know, in linear regression, we need to get rid of the variables that they can have a strong correlation between them. Otherwise, linear regression is going to underperform. We are going to select our independent variable to deterministic process attribute by in sample. And then we are going to calculate our forecast from out of sample with a window of 9 steps further. Let's see if I could write it right, or I forgot. Oh, I didn't I didn't close my deterministic process. Oh my gosh, another error. I'll drop in because I missed one P. Sorry about that. Oh my gosh, another error. Many of you can get identified with this. It's dropped. Sorry about that. It's dropped. Finally, we got it right. Yay. Okay, now we are going to run this linear regression. We can see here the linear regression and the 90-day forecast in red one. As we see, this forecast is following the trend of the previous data, or the blue line here, and it's having like a downward bend. And now it says one way to fit more complicated trends is to increase the order of the polynomial you use. To get a better fit to the somewhat complicated trend in store cells, we could try using an order 11 polynomial. They are asking us to run the cell, which they changed the polynomial order of 11, which is a little bit elevated. As we see now, our model is just diverging negatively for the next coefficients here. And then it says, understanding risk of forecasting with high order polynomials. High order polynomials are generally not well suited to forecasting. However, can you guess why? The first that we can think about is that linear regression works best in linear relation between features, as the name says, linear regression, right? It doesn't set good boundaries of models for linear, for superior above of order of relation, like quadratic or cubic. There are other types of algorithms that work with this, like support vector machine. And also a little bit in the slides, we are going to see why they don't work very well. So let's check what they say. An order 11 polynomial will include terms like 10 to the 11 order, and these tend to diverge rapidly outside of the training period, making forecasts very unreliable. And now we are going to see why. As we were seeing here, it was going downwards. Now it went terrible here. And also this happened very common in when you set high parameters or very extreme parameters of your ARIMA models, where you're using like extreme P or Q parameters of your ARIMA models. What it does, autoregressive integrated moving average models, is to diverge down or up. And now I will explain why superior order of linear relation don't work best. When to use linear regression? Why linear regression is not a common forecasting technique? Linear regression assumes the series are independent of each other and they are equally distributed. Otherwise, in time series data, points near in time tend to be strongly correlated with one another. In fact, when there aren't temporal correlations, time series data is hardly useful for traditional forecasting methods. When to use linear regression? We are not going to say that don't use linear regression for time series applications or approach. You can do it only on very specific conditions that there are. The time series has a linear response to its predictors. No input variable is constant over time or perfectly correlated with another input variable. Assumptions with respect to the error. For each point in time, the expected value of the error is 0, and the error at any given time period is uncorrelated with the inputs at any time period in the past or future. Also, the variance of the error is independent of time. What could go wrong if we force linear regression for high order polynomials or for forecasting? Some of the consequences of applying linear regression when your data doesn't meet the required assumptions are: our coefficients will not minimize the error of our models, and also the p-values for determining whether the coefficients are non-zero will be incorrect because they rely on assumptions that they are not met. So this is a warning that that's why linear regression is not very used for forecasting approaches. Here in Kaggle, they do this feature engineering of converting data points into dummies. That's why it works. But as I said, in the classic time series or forecasting literature, you're not going to find linear regression that often. Now we are going to go to the next topic that is about seasonality. What you need to know about seasonality. In time series, we can find them as a recurring behavior at a certain fix or frequency, impacted by human demand, weather, or time of the year. For example, ice cream sales in a year, the highest sales happen in summertime because everyone to gets a refresh, right? But in winter, the sales of ice creams goes down because everyone wants to go see up, right? Then a daily seasonality in restaurants, they have the highest traffic on breakfast, lunch, and supper time, while they don't have too much activity in the meantime of those periods. What happened when we want to buy air tickets in flights? The prices go higher to the demand during the holidays, right? So it's how seasonality works. And now I will to show you how it's like with ice cream. On a year that ice cream, the high sales, as I said, it happens on July, August, and the lowest sales happen on December or January. That is what you need to know about seasonality, because here in Kaggle, they will go a little bit deep. Seasonality, in Kaggle, they use feature engineering using Fourier series. Fourier series, what they do is to a time series is a function of time. And with Fourier series, you convert from the time domain to the frequency domain. So a Fourier series is the practice of describing a function as a series of sines of cosines. There are well-established ways to feed a Fourier series in NumPy, in Python, and I just dropped this formula as your reference, how they convert from time domain to frequency domain. And also in the next slide, dropping the inverse Fourier, so you can get from the frequency domain to your original function in terms of time, and also dropping this for reference. You can check it out later. And in the Kaggle tutorial, they show us about a periodogram. A periodogram of a time series is an estimate of how much different underlying frequencies contribute to the time series. A perfect periodogram could translate a time series from the time value phase space, which we most commonly work with, to a power frequency space whereby a time series would be described in terms of how much it was shaped by recurring processes at various time steps. There are many ways of computing periodograms. One definition and computational method is the Fourier transform, as we saw in our Kaggle, as you will see in the Kaggle tutorial. We have this periodogram in the 3-axis plane. We have our x, that is the time, are those sinusoidal and cosinusoidal waves. And here we see the spectrum here on frequency domain on the y-axis, and the amplitude goes like upwards or downwards. Another way that we can interpret a periodogram, we have these 3 types of waves with different frequencies. We have on the blue one, on a frequency 1 that is not more, is a low frequency, as we see. Also in the magenta, we have a high order frequency, and the green one is a higher frequency of 10, and the yellow wave is the total of the sum of these 3 frequencies. And we can see here in this periodogram how we interpret the periodogram. Now we are going to see it on Kaggle. On the x-axis, we have the time domain. On the y-axis, we have the frequency, all these waves, and the amplitude goes up. I drop here the customized function of how Kaggle feature engineers the time series in Fourier terms, but also you can do, well, I will show you later, but then what they do is to use calendar Fourier. Here you use your largest time scale. Let's say in this case is annual. It can be annual or it can be monthly. While in the deterministic process, you compute your seasonal indicators or dummies for your seasonal on a smaller or repetitive scale that it can be daily or weekly, right? sorry, again. And here we select our independent variable with the attribute of deterministic process in sample. But also you can apply the Fourier series through NumPy with the fast Fourier transform, where you can get your coefficients with the following methods. So I'm dropping here for you for reference. Yeah. Now we are going to jump to our exercise. We can go to seasonality now. We're going to run this cell to setting everything up. It didn't run. What happened? Now they're doing this data conditioning to show us the seasonality. What they do is group the sales. They have days and also the sales. And what they do is group by week. Here in this legend, which is a horrible visualization, by the way. But in a period of 8 months, they show the sales of each day of the week. And we can see the highest sales or seasonality happen in Saturday and Sunday, and basically on Saturday and Sunday is where sales goes up during a week, while in Monday, Tuesday, Wednesday, Thursday, the sales are not so good. It's because normally people they want to go more shopping on weekend. It's because they have more time, right? Now they are going to they want to show us the periodogram of the average sales. This is how I explain the periodogram, how to interpret it in the slides. We see that semi-weekly, weekly, bi-weekly, monthly, they have the highest variance, and in Christian terms, it means that they are going to add more information to our models through the variance, right? And now they are doing the following question. What kind of seasonality do you see evidence of? What seasonality you see here on this periodogram, guys? Okay, well, just to make it more quickly, it's just weekly, bi-weekly, and monthly. They have the biggest activity, and they will give more information. Also, I just want to specify that I just want to make clear that the variance of a periodogram at a particular frequency represents how much information we can bring to our models, right? And why, let's see the answer, and I will explain you why they don't choose half week. It says, both seasonal plot and the periodogram suggest a strong weekly seasonality. From the periodogram, it appears that there may be some monthly and biweekly components as well. In fact, the notes of the store sales data said that people get paid on the 15th day and the last day of the month. As we see, this is the 15th day and this is the last day of the month. As I say, we have a strong component on weekly, and semi-weekly is reflected here on Saturday and Sunday, that are the weekends. And why they don't choose this one? It means because we need to create a higher, bigger number of dummies. And in this data set, it doesn't apply, but for larger data sets, it means your models will run slower, and we need to use more computational resources. That's why they only use the weekly and biweekly and monthly for seasonality. Now, they are asking us to create the seasonal features use deterministic process and calendar Fourier to create indicators for weekly seasons and Fourier features of order 4. They make a copy of the average sales. And then, as we saw on the slides, we use the calendar Fourier to describe the seasonality, the annual seasonality in terms of, the monthly seasonality in terms of sines and cosines pairs. Frequency of 4, as we were, it's a monthly, and then the order of 4 as it was requested on the exercise. Here, we are going to create our seasonal indicators using the Y index. The constant equals true, and then it's going to be a linear relation or linear relation between variables. And then here we are going to create our seasonal indicators. And then here we are going to add the Fourier series of the monthly seasonality on additional terms. Then we are going to select our independent variable. Sample, put, and we're going to check if we got it right. Oh, okay, I missed the Fourier. Oh, another. Oh my gosh, I know what was wrong here. Just I needed to add the Fourier. Yeah, we did it right. So now we are going to run the linear regression with the seasonalities. We could see that the seasonalities could capture a good amount of sales of this graph, and it only filter like, let's say, outliers of extreme values. Removing a series, its trend or seasons, is called detrending or deseasonalizing. Look at the periodogram of the deseasonalized series. Here they doing the detrending, which it subtracts the prediction from the original target values. Let's see how it looks like. They compare the original periodogram with the deseasonalized graph. We see that it got rid of all the seasonalities, like the monthly, bi-weekly, the weekly, and semi-weekly here. Now, check for remaining seasonality. Based on these periodograms, how effectively does it appear your model capture the seasonality in average sales? Does the periodogram agree with the time plot of the seasonalized series? It looks like they capture all the seasonalities here, and let's see the answer. Correct. The periodogram for the deseasonalized series lacks any large values. By comparing it to the periodogram for the original series, we can see that our model was able to capture the seasonal variation in average sales. Now we're going to go a little bit more fun part, that it's about the holidays. The store sales dataset includes a table of Ecuadorian holidays. Now we are going to see what are the most important festivities in Ecuador. They don't differ from US or Canada. They also celebrate New Year's Eve. My favorite is the Carnival at the end of February. The annexation of Cotopaxi province on April 1st. They also have Holy Friday, Mother's Day on May 13, you name it. Now we are going to interpret it in the next plot. Here we can find the carnival. On April 1st, what they have the Cotopaxi promise annexation. And they also, in May, they have a lot of holidays. They have the day of work, they have Mother's Day, they have also the, let me check, the Pichincha battle, etc. Now, create holiday features. What kind of features can we create to help our model to make use of this information? So let's see. For these holidays, we only need to create normal dummies. We can do it through get dummies or one hot encoder. Now we are going to solve this exercise with pandas, get dummies, holidays, and they are going to add these new dummies about the holidays to the data frame. Let's see if we got it right. We got it right. How this data frame looks like now. Let's see. But I always need to see how my data looks like after a transformation. Here we can find the constant, the trend, the Fourier series, and the holidays are converted into dummies here. As we see, they are talking about the New Year's Eve. And yeah, and that's it. Now we need to run the linear regression to see how much information could bring to the model. Now the holidays gave a really good hints on how to forecast the sales, and we see that they could give us better hints. It captures most all of the information and just left some few extreme values. Now we are going, and yeah, and that was all for my part. I'm not going to cover how to submit the store sales competition because I want to give the Vipriya time to show us modern forecasting techniques. And thanks for your patience and stay putting with me. It was a pleasure.
So much, Vania. It was very informative.
Thank you, Chaima.
Okay, so yeah, let's welcome the Vipria. You can start share your screen. Yeah, and take over from me.
Uh, is my screen visible?
Yeah, just
All right.
slide.
All good?
We can see before your main
You can see your
presentation.
screen. Yeah.
Okay, yeah. So, hi, everybody. I'm Devi Priya. I am, today we are going to see about time series analysis. Uh, and as already, the intro was given by Vanya. Uh, Now we'll delve more into the ML concepts. So today our contents would be time series as features, forecast. Oh my god! Okay, forecasting with YAML and hybrid models. So I'll start with the introduction. Now, like, what is meant by time series? Time series forecasting is actually a blend of art and science. And while it can never predict the future with 100% certainty, it actually provides a data driven insight into potential future outcomes. So, machine learning enhances the traditional time series techniques, so bringing the power of algorithms to capture the complex patterns and make more accurate forecasts. So, as with all, the ML endeavors, iterative refinement and understanding of domain specific nuances are crucial for the success of the time series analysis. So to give a short intro of our time series, we have a sequence of data points indexed or listed in time order, and then we have you know like we have successive data points taken at successive time series, and then they are all equally spaced, and then we are going to forecast. uh, More than forecasting, I can use the word predicting. We can use one series of uh, data to forecast or predict another series of data. That's a very simplest explanation. So, importance of time series forecasting. We can see, in business planning, the stock, sales, and resource allocation, all these points that I have listed out in my slide. I'll be giving you the slide. So I'm not going to really, read out the whole slide. So bear with me over there. So the points that I have mentioned here, science and medicine, the weather forecasting, the epidemiology predictions, all these, are important applications of time series forecasting. And being in the field for so long years, I personally feel it is one of the important topic to cover. And the results that the time series occur, they are they make a huge impact in all these fields. So we'll delve into time series as features. So the first topic would be like time dependence. So time dependence is actually a broader concept encompassing any relationship between a data point and time. So this includes, trends, seasonality, and several other patterns. And there is more, like a general term that indicates a relationship between variables current value and time. So while serial dependence specifically looks at relationships between the data points at different time lags, time dependence encompasses a broader set of patterns, including the trends, seasonality, and the cycles. A time dependent series, it doesn't necessarily have the serial dependence, but a serial dependence is by definition a time dependence. To you know like to know about serial dependence, I'll just give you a brief definition about serial dependence. So in statistics and econometrics, serial dependence actually refers to the scenario where the values of a time series are completely correlated to its past values, meaning the values at the time t is actually depends on the values at the time t minus 1, t minus 2, and it goes on. So that's the short definition of serial dependence. This serial dependence is actually, this term generally refers to the relationship of a data point in a time series and its preceding data points. A common tool to check the serial dependence is the autocorrelation function. And if there is no, serial dependence at all, in the data, then the autocorrelations for all the lags except the lag 0 should be 0. So if we see here, in the time dependence, you can see these patterns of data when you plot the data points on the time, keeping the time as the x value, you can see like a trend or seasonality kind of things. So say, like as Vanya explained, say we have the ice cream example, and you can see there would be a spike in the plot when it comes, like when we plot it against the seasons, and like in summer we do have a spike. So that kind of uh, business, depending on a time That's what, like these concepts comes into uh, picture, and they play a huge role. So here, these are all the data points, and we just get plotted against the time, and you can see certain patterns here. So this is how the time dependence plot looks like, and this is serial dependence plot, meaning, say we have unemployment rate, and it is plot an unemployment rate at time t, when it is plotted against the unemployment rate at time t minus 1. And if you see this kind of correlation, this is called serial dependence. And if you see, like any such patterns, this is called serial dependence. So you can see here it's a lag 1 target, and the y-axis should be target. And the next one is the cycles. Hope you can see. Yeah. So the cycles is actually a serial dependence to periodical patterns or repetitive fluctuations in the time series data set. So when a time series has cyclical patterns, observations at a given time period, like it might be correlated and with the observations of the previous time period, the lag. So that is one cycle or multiple cycles before. So this is a short explanation of cycles. So it is actually often driven by the economic conditions, such as the business or like the financial cycles. You would have seen it, in all, mostly the cycle pattern is something you can often see it in stock examples. Mostly it's used in financial industry, and it's also like one of the components in time series. So as explained by Vani already. So here you can see, like how it is. So we can actually see, like there are certain spikes, and we understand that this has a seasonal component in this. So this bunch of seasonal components together, when it is get tied together, they are called cycles actually. And we'll come to lag series. So the definition of the lag series would be, lag series is the same data set shifted backward by a certain number of periods. So for example, in a daily data, a lag of 1 day would mean that yesterday's data is used today. So why is this actually important? you know, Many time series models like ARIMA actually rely on the relationship between an observation and a number of lagged observations. And also, it actually helps to determine the past values that influence the current values. Also, in machine learning, lagged variables can be used, like to feature the training models. So, to create a lag series, we actually have few like few ready-made functionalities provided by pandas. So as explained already, we have this shift function through which we can create the lag series. So here we can see y is the employment rate, and we are creating lag 1 and lag 2. We're shifting it 1 and shifting it twice. So you can see here how the lag series works. So this is the y column, and the lag 1 would be, the first record would become the second record, and in lag 2 the second record here would become the third record here. So that's how the lag series work, which means if you take this record for 6.1, the lag is, the previous value in the same series, that is 6.0, and the lag 2 would be 5.8. So I hope you understood this. If I am, like going a little super fast or something, please leave a message, in the chat. I'll back up. And now we'll enter into the lag plots. So lag plots, like are a diagnostic tool to actually visualize to actually visually check for autocorrelation in the time series. So they are constructed by plotting the data like yt against its lagged values yt minus k, where k is actually the lag. So importance of, like this diagnosing the autocorrelation would be, this actually refers how correlated a series is with the sparse value. So detecting this autocorrelation can actually help in selecting appropriate models and interventions for time series forecasting. And this is the lagged plots. If you can see, like how it is getting clustered along the diagonal. So if a point in the lagged plot cluster along the diagonal from bottom left to the top right, this actually indicates that it is positively correlated. So when it is positively correlated, it means that the past value increase and the current value also increases. So this is the past values and this is the current values. When these increase and this is also increases, and this is something, like very important when it comes to time series. And the patterns we have here is called linear pattern. So you guys are all have been already been introduced to linear regression. So this is one of the finest example. And when this plot goes on the opposite end, from bottom left, is this bottom left? No, sorry, from top left to bottom right, if we have this line or clusters aligned from top left to bottom right, then it is called negative correlation, which means that the past value increase and the current values tend to decrease. So that is one of the type. And another type would be, like randomly scattered. If this, like cluster of data plots is randomly scattered without any discernible pattern, then there is no actually clear evidence of autocorrelation. In such cases, you should think twice before using time series for such data. It doesn't make much of the sense if if the cluster is all scattered all over the place. And the fourth one is the elliptical scatter. It might suggest a sinusoidal pattern, means a cyclic behavior or seasonality in time series. And well, if we want to talk about the applications of lagged plots, they actually quickly, like it's a visual check basically on the nature of the data. So it's actually very useful for the preliminary data analysis. So whenever you are starting up with the time series analysis project, it is a best approach, and it's a recommended, it's a very important point to test the lagged plots between the current data and its previous data. So now with partial autocorrelation plot or the correlogram. So the partial autocorrelation actually measures the correlation between the time series and its lagged values. So with an essential distinction. So it means it controls the correlations at the shorter lags. So thinking of it as looking of the relationship between the time series and its lagged values, while ignoring or removing the influence of all the intermediate lags. So say if we have lag 3 and we have the current data, and we are trying to plot a graph. When it is lag 3 and the current data, this partial autocorrelation plot can show how lag 3 is related to, or how much it affects the current data uh, without it getting like disturbed or affected by the lag 1 and 2. So that's the short explanation of partial autocorrelation plot. I'll explain it with this, this. Okay, sorry about it. So here is the graphical representation, and here we can see that, my God. So here we can see that on the y-axis, it represents the partial autocorrelation value, which actually ranges from -1 to 0.1. And this is like a typical correlation coefficient. And from the y-axis, sorry, from the x-axis, you can see it represents the lag number, signifying, like which lagged version of the series we are considering. And this is like for lag 1, this is lag 2, this is lag 3, lag 4, and it goes on. And here we have plotted for 1 to 12 lakhs. And this blue band, if you see here, there's a blue band here. So this blue band is actually represent the statistical significance band. Like I'll explain you, like how it works. So we can see, like there are bars or spikes on the graph that exceed, these significant bounds. So the spikes that exceeds this significant band is actually called, like they are all noteworthy partial autocorrelations. For example, in this case, we can see, the lag 1, lag 2, lag 3, lag 4, lag 5, lag 6, and lag 11 have actually exceeded this blue band, which means that we can consider them for a time series analysis. But if you see here, the lag 7 to 10, they didn't exceed this blue band, which means that it's not worthy to consider them when you want to do the time series analysis. But if you see the lag plots for those similar lags, you wouldn't be able to identify any of those things, because they are all almost, like they look alike, and it appears to be they have some correlation. But that's not the case if you look at the partial autocorrelation plot. So it is very much advisable to use the partial autocorrelation before you enter, like with the machine learning models, and then select your lags. And then, like that's how the feature analysis has been done. And then we'll come to the topic deseasonalization. So one of the fundamental tasks in time series analysis is to actually remove or adjust the periodical fluctuations, so commonly known as the seasonality. So why should we actually remove seasonality? This seasonal fluctuations can actually overshadow the underlying trends or patterns. So by removing them, we can actually better visualize and analyze these underlying components. So for instance, a retail sale might spike every December due to the holiday season. By removing this seasonality, we can actually better understand the non-holiday factors that influences the sales. So, and there are actually a lot of methods to do this. Some, like few of the methods can be moving averages, or like differencing technique and STL. They are all very advanced techniques. So I'm just mentioning, I'm just mentioning the names. Let's not dig deeper into that. And what would be the, like the benefits of this deseasonalization? It actually exposes the underlying trends. And like apart from seasonality, data might have a longer term cycles of fluctuations. So without the noise of seasonality, there can be actually, they can be actually more easily identified. So, and also some of these time series models require the data without the seasonality. So deseasonalized data is often like more amenable to modeling and can actually lead to more accurate forecast. And go to leading indicator. So leading indicator, like when discussing the time series data, sometimes there exists a series that leads another, giving the early indications or warnings about the future predictions or trends in the later series. So this leading series is actually a pretty measurable set of data points that begins to change or manifest a pattern before the second series start to exhibit a particular trend or behavior. So if you see in this example, we are actually plotting two columns, so flow curve and flow visits. So if we see the flow curve and flow visits, the trend, the seasonality, like whatever time pattern it follows, it is the same for both of these columns. Meaning, if we do not have the data for, say, fluke curve, the blue band here, if we do not have the data, we can still use this flu visits to identify what kind of pattern it might, like take at this part of time. So that's called leading indicator. Basically, we have got two columns, two different columns, which is not a lag columns. It's just two different columns, and one column can be used to predict the future events of another column. So this is called leading indicator. Okay, so now we'll get into the tutorial.
While
So this is
just a little bit second. While the Britvilla is setting up, we invite you to fill in our survey so you can win a Chromecast. And also for the Edmonton residents, you can enter to another raffle when you are SPP for Google I/O Extended. I just dropped the links on the chat. And yeah, so you can win another Chromecast. Thank you. Sorry about the interruption, the Britvilla.
this is fine. So we'll get into the exercise part. We have a data of store sales, and we have got average sales and store sales. This average sales is nothing but the store sales that has been grouped by the date. So I ran this. We'll just see how it looks like. So it's the date and just the sales. So ensure, like before you start any of the time series project, ensure this is sorted. The dates must be sorted. And here it has been, like it's plotted, the hardcover has been plotted against the time series. So we can see it's a linear regression, and there is a trend going forward. I mean, it is going upward. So there is a positive autocorrelation here. I think I took a wrong one. Sorry about it. I took linear regression. Okay, I think it's already been covered by Vanya. Sorry about it. Okay, here we are actually considering the family sales, and this has been actually a data frame where it has been grouped. The store sales has been grouped by the family and the date. So if we see how it looks like, okay, we have got different families. Meaning, by family they mean, the automotive, baby care, beauty, beverages, and etc. So these are all for sales, and it's the same family but for on promotion, and the dates are already been sorted here. So here they actually mentioned that not every product family has the sales, so showing the cyclic behavior, and neither does the series of average sales. So we'll just, like, so this is actually, I'll explain this. So we have the supply sales for this family, school and office supplies, and we have the Y series, meaning just the sales, and we have the Fourier series here. So the Fourier terms can actually capture the cyclic patterns in the data. So here the calendar Fourier is actually set with monthly M frequency and the order 4, meaning it will use the first 4 sine and cosine terms to model the seasonality. And we have the deterministic process here. So this sets up for, the modeling time series components. So the important things to note here is the constant is true, and the trend of order is 1, meaning it's a linear trend, and we have several, seasonal components here, and we use the previously defined Fourier transform here. So x in time. So we know what's mean by the in sample. So it actually generates the deterministic components for the given index. So a new column is actually added for, okay, this is for the next line. So we have the X time, and for this X time, we are having a new column, New Year's Day, so which might have some effect on the sales. And then we are doing a linear regression. So we are fitting the model by taking the X time as the features, and the Y from here, which means the sales as the Y part, as the target basically. And then we are deseasonalizing here. So the fitted values, the seasonal components and the other deterministic components from the regression models, these are the other other components from the regression model are subtracted from the original sales data. This is the original sales data to get the deseasonalized sales. So as I have already listed out the several methods for deseasonalizing, the one that we are using here is differencing. So we name it as sales deseasoned, and when we plot it, we can actually see the cyclical components have been retained, but there is no seasonal components here. So that's how a deseasonalized plot looks. So here, we are going to create a 7-day moving average from Y, the series of the supply sales. So we are using a centered window, but they are advising don't use the min periods argument. Okay. So using ruling, and window is say 7, and they advised us to use the center. True. And this is mean, it's a moving average, so we use the mean on top of it. And then if you run here, we can see how it looks. So this is your 7-day moving average for this data, and you can see, the cyclic patterns have been retained everywhere, but it's a smoother version. So when you calculate average and when you try to plot it over in a graph, it would give you a smoother version of your original graph. So here, yeah, we have your the partial autocorrelation plot here. So we can see, the blue band is here, and the partial plot has been done for 8 lakhs. And we can see that 0, 1. So the first plot and the 8th plot are the first lag and the 8th lags are the only ones that that's happened to be noteworthy here. So when we are using this YD season as the data for time series analysis, the lags that we are supposed to consider is the first one and the 8th one, and we can discard all these 2nd to 7th lags. But then if you see the lagged plots for all these lags, they're all look very much alike to each other, and they appear to be very much useful, but actually they are not. So I would really suggest put on the lag plots and then go for your partial autocorrelation and then select your lags for the project. So the second topic is examining the serial dependence for the store sales. So are any of the lags? Yes, we saw this on the Periodogram. Now we are using the concept of leading indicator here. So they are considering the on promotion, what do you call it, the on promotion index as the leading indicator here. The reason being, the company itself decides to do, decides to do the promotion, and they decide when to do the promotion. So there is no worry about the look ahead leakage. Meaning we could use actually the Tuesday's on promotion value to forecast the sales on Monday. So this on promotion has been, like we are trying to use this on promotion as the leading indicator for the sales. So we'll run it. Sometimes it just happens. So we are, like we can see the on promotion and the sales decent on the y-axis. So we can see that there is a good amount of correlation for the on promotion and the sales decent. And we are, like the one important point to note in here is we have got 4 lag plots and 3 of the lead plots. Lead plots in the sense, in future, yeah, so lag plots is t minus 1, t minus 2, t minus 3, and lead plots would go like t plus 1, t plus 2, and t plus 3. So does it appear, that either leading or lagging values of on promotion could be useful as a feature? It appears to be, like correlated. So I think for now we can take it as, like noteworthy features for doing the time series analysis. So here we are trying to create the time series features. So you can see make features from Y season, and it's X lags. So we can make the lags from Y season, and the lags is equal to 1. And make the features from on promotion, and you may want to use PD contact. So here we are trying to merge columns by making, merge the columns from on promotion and the lag series and the lead series from on promotion. So we'll start with lags. So make lags of, like on promotion. Yep. That's equal to 1. And we'll insert on promotion 2. And we'll make the lead version of on promotion, which is equal to 1. And then we have to put it together, concatenate it on axis is equal to 1. So do not forget to mention that. Sorry, it's leads if I'm not wrong. Okay. So here we are doing the training and test data split. So we are having the training test data split and the X and Y as feature and target. The test size is 30%. So no, it's actually 30. So we are having the X train, X valid, Y train, and Y valid. We are creating the linear regression model here and try to fit the X train and Y train. So here the Y fit is PD.series model.predict. So we are using this model to predict the X train. And then this clip part means clip of 0. I'll tell you what it does. So if there are any values above 0, below 0, meaning any negative values, -2, -3, that kind of values, it will round it to 0. So that we will not have any negative values in Y fit. So it's the same thing with Y pred. We are predicting the X valid. And then here we are trying to find the RMSLE. It is something like a measure of accuracy kind of thing. So we are using this RMSLE to see what is the error between our actual values and the predicted values. And it is the full form is mean squared log error. We are trying to find it for y train and y fit, and for y valid and y predict. So if we run this, oh, we've got some error. It shouldn't be the case. Did not run anything. Oh, it's lag. We have got series. Make leads on promotion. I'll do a quick check on yes. Okay. Okay. We have got some. Okay, we've got some null values here, and that's why it's like throwing up. So we'll do the drop. It should work. Yeah, okay, so what happened was I have got some null values in x-axis, sorry, in the x data frame. So I did the drop in here to drop all the null values. So now it should work. Yes, so here we can see that the training RMSLE, which is 0.83, and the validation RMSLE, which is 1.17. Usually when the training RMSLE is like lesser than the validation RMSLE, which means like generally it's overfit. So it's a machine learning concept. I don't want to dig so much deeper into it for now, but usually this is overfitting and we have to do something about the data that we are trying to work on with. So now we'll create the statistical creatures here. So what they are asking is 14-day rolling median of lagged target. So we have this mean. It has been already created for 28-day mean of lagged target. So we have this using the rolling function for 7 days. We have found the mean, and we are assigning it to mean underscore 7. So we'll do it a similar job for median 14. And for we have to find the standard deviation here. And here we are using the on promo. So for all these data, we used the Y lag, but for here we are using the on promo data. The sum of the proportions. Okay. So they have asked to use the center. So we'll mark it center is equal to true. and the sum of proportions. So we'll make it sum. Should work. Okay. So that's it with time series as features exercise. So we'll get back to this. So, okay, we'll start with hybrid models. So, the trend actually represents, okay, we have got many components of time series, and we know that, the trend actually represents the general direction in which the time series is headed over a prolonged period. And the seasonality, it refers to the predictable and repetitive fluctuations in time series that occur in regular intervals. And the cycles are long-term fluctuations in time series, often extending, like beyond a season or a year. And this new component, irregular or residual component, it generally means, like it actually captures the random and unpredictable changes in the time series, for accounting, after accounting for trend, seasonality, and the cycles. So these four are the components of time series. So here we can see, we have plotted the data points of, so data points against the time, and we can see a trend here. So if we remove the trend component in this plot, we would get this seasonal plot. So after, like calculating the residuals, if we remove the seasonal component from this graph, we would get the cycles plot. So this is the cycles plot. This blue band is the cycles plot, and this gray band, if you see, these gray band are the predicted values basically. So the difference between this predicted values and this blue band is called residuals, meaning the error. So if we remove even the cyclics pattern from this plot, we would get this plot. So I'm repeating once more. So this is the original data, and it is plotted against the time series. The time data is plotted against the time. So this shows the trend, and if the trend component has been removed from this data, we would get the seasons, and when the seasons component is removed, we would get the cycles. When the cycles component is also removed, we would get the error. So this is how this is how the flow goes. Again, like the residual part. So difference between the observed and the predicted values in the model. Here you can see, this blue band is the observed one, and this gray one is the predicted one. So difference between the blue and the gray is often called as errors or residuals, and that is when, when you plot the errors or the residuals, it forms a plot like this. Okay. Now one might actually, ask, like, what's the significance of these residuals? So when an irregular component is, inherently being unpredictable, you should be aware that it is actually vital, and it reminds the analysts or the decision makers about the inherent uncertainty and the volatility or in the time series data. That emphasizes the importance of the flexibility and the adaptability in the strategies. So the next one is hybrid models. So this first step, basically hybrid models means, you use more than one models to predict. So here the first, the objective is the first step to identify the suitable forecasting model that aligns with the main features of our data. And this is our, like the foundational model. And the importance of this is, this initial model actually captures the bulk of data structures such as, the trend and the seasonality. And by fitting the primary model, we actually provide a baseline for further refinements. And then after doing this, we compute the residuals. So the residuals, as I have already mentioned, it actually represents the difference between the observed values and the values predicted by our primary module. So once we, calculate the compute the residuals, we take this residuals as input for the second model. So here, the model, we are basically using the second model to model the residuals, essentially addressing the patterns and structures of the primary model that might have, like the primary model might have missed actually. So basically what we are doing is we have a data, we are modeling it using one primary model, and then we get, we do the prediction and we compute the residuals by differencing the predicted values and the actual values. Once we have the residuals, we pass it as input to the next model, and then the next model comes up with the, again we can predict new data with the second model, and the second model can capture the few minor details that the first model have missed. So that's when, through hybrid models, we are actually capturing all the data that a time series data set can give. So this is what I explained. And there are two types of hybrid models. So one is model stacking, and another one is boosted models. So model stacking means multiple base models are actually used to produce intermediate predictions. Meaning, so one model actually takes the prediction of another model as input. So that's called model stacking. But with boosted models, what happens is you use the residuals of the base model, and then with the help of residuals, we use the second model, and then it produces the predictions. That's the difference between model stacking and model, boosted models. Basically, the model stacking uses the second model. In the model stacking, they use the intermediate predictions, but the second model in the boosted models, they use the residuals. So that's the difference. And we'll start with the exercise. So again, we are using the family sales here. So here we are defining a customized class, boosted hybrid, for using two models, model 1 and model 2 here. And here we are defining, the fit method for the boosted hybrid. We already know the purpose of this fit method. So it's a readily available method to do the fitting the fitting functionality on a model. But here we are, customizing it. So we'll define R1 fit model. So your code here, fit self model 1 means self. Is that correct? We have our, so for model 1, we pass the x underscore 1 and y as the components. And y underscore fit is equal to PD data frame, your Fourier, make the predictions with self model 1. Okay. Self model 1, predict x underscore 1. So here we are supposed to compute the residuals. So again, what is meant by residuals? So you compute the difference between this y fit and y. So y minus y fit. So once you compute the residuals, you squeeze it so that it would become into a single column. And here you fit the self model 2 on this residuals. So this is called boosted hybrid. So this is the example for boosted hybrids. So we have to do the residuals. So we use x2 and y underscore residual as the components for this model to fit. So we check in here. Okay, there's some error. Y_receives now. I think I didn't run some, some of the code in Prior. So, okay, something is wrong. Okay, it's all fine now. So something is wrong with the Kaggle exercise, but otherwise, along with the code, it's all fine. Now we are actually creating a customized predict method. So def predict ypred is equal to, we are creating a data frame that has the predicted value of self model 1. Means self model 1, we do the predict part, which takes x1 as the input, and then we have your ypred. So once again it is tagged and squeezed, and here we are supposed to do the model prediction for the model predictions for model 2. So add the self model. Okay. We have to do predict. So okay. So here we have, to summarize this again. So we are predicting with self model 1, and we have this, like, ignore this actually for now. So then we add the prediction of x2 to this prediction of model 1's predict, like ypred. So this ypred now has both of these results, the predicted values of x1 and predicted values of x2. Okay, it's incorrect. What did we miss? So let's wait 2. It's column x2, it's right. It's ypred stack squeeze. Model 2 predictor 2 more should work. Sorry, not late. It happens sometimes. So please bear with me. Two. Okay, here itself is incorrect. So we have this predicted one. Okay. That's where. So I did is equal to instead of minus. So yeah. Now it's all fine. We now defined we actually defined the customized predict method. And now we are ready to use the boosted hybrid class here. So we have this target series y. So I'll just show how does the Y occurs to be. So this is the whole Y. And here we are considering only the sales part. So we actually saw in the previous code snippet that we actually had two parts, two indexes, sales and on promotion. And here we are displaying only the sales part. And then, like we are creating the features for this linear regression X1 using the deterministic process and in sample. So we have got X1, and we are actually also creating the X2 part by dropping the sales and stacking it. Means this X2 is on promotion. So we have this on promotion part 2, right? So we are assigning it to the value X2, and then we are doing the label coding for the families. So finally, after we have this X2, we'll actually see how does the X2 looks like. Cool. So we have this date sorted, and the families are all labeled. It's all encoded to 0, 1, 2, 3, meaning 0 means automotive, and 1 for baby care, and 2 for beauty. It falls into that series. And we have got the on promotion sales here. And again, these, the day is actually reflecting the days from this date component. So if it is 1, it is 1 here. So if it is 15, it is 15 here. Now we'll train the boosted hybrid. So for this, hold on a second. So, okay, what's the name of, okay, the name of the class is boosted hybrid. Let's see, boosted hybrid here. And they're asking us to use linear regression and XGB regressor here. And we can do the model fitment method here. So it takes 3 components, X1, X2, and the Y. And here we can do the prediction, means model dot predict for X1 and X2. Oh, it's all right. And here they are trying, and like they're asking us to implement some other more combination of 2 other models. So we'll just consider rich model, and what else? We'll consider this k neighbor regressor. And then again, we are doing the training and we are fitting it. So this is the final plot. So here you can see, like these are all the data that we have, and this is the data that it is predicted. So this red line is something it predicted for each of this family. And you can see, this red line is not a exact combo of or an exact reflection of what the actual sales are. So we can see, these gray plots. Yeah, so these gray plots are the actual ones, and we can see that the red ones are, like a little bit, it's a little bit different from the actual ones. So yeah, so that's all with this exercise. So let's move on to the forecasting with the ML part. So what, like, to start with the forecasting of, like with ML, this is actually a shift in the forecasting paradigm, meaning the traditional statistical forecasting methods actually involves with the advent of ML. And this ML actually introduces the flexibility and can harness large amounts of data, potentially improving the forecasting accuracy. So mostly for time series analysis, we use statistical forecasting methods, which are quite, like a little different. But now, like we go with advanced topics with ML, which gives us better forecasting accuracy. And there are a few points to be noted. So the first one will be, like what information is available at the time the forecast is made, meaning, like the X part of the model. So what are the features are available for us to make this forecast? And the another important point is, what is the time period during which you require the forecasted modules values, meaning say if we have the data for January to July, and we want the forecasting information or the predicted values for July to August. So this July to August will be your target. So these are two important things that you have to note. And the next important point is forecast origin. So before diving into the mechanisms of the forecasting, it's essential to identify our start time. So the exact moment or point in which the time which we initiate the forecast. So this is often termed as forecast origin. So we can actually say this as a moment of initiation, and like think of it as an anchor that routes our forecast in the real world. So it serves as a bridge, like between the known data and the future predictions. uh, the importance of this forecast horizon would be, it actually determines the data availability and the temporal boundary, meaning it actually sets a clear boundary delineating the past and the future. So by defining this point, we can also clarify the forecasting horizon, that is how far into the future we intend to make the predictions. So this is forecast horizon. I think it got confused. Okay, like I'll explain it with this plot. This would be more easier. So this is the data that we have, and this is called forecast origin. This point is called forecast origin. So this is the point till which we have the data, and this is the point. These red line, this red line. So this is the point where we are going to do our forecasting. So this is called forecast horizon. So the difference, the number of time steps between the forecast horizon, the starting point of forecast horizon and the origin is called lead time. So here the lead time is 2. So 1, 2. So here the lead time is 2. And if you prepare, like, so we have to prepare the data set if you want to do the forecasting. So say, we have the y step 1 here. So the features would be, like we are making y lag 2. So you can see y lag 1 is missing here. So if we have y lag 2, meaning consider this third record. So we have this value of 2. So y lag 2 means we can go, we can take the value that has been lagged 2 years prior to this value. So the value y lag 2 value for this 2 would be 0. Y lag 2 value for this 3 would be 1. Y lag 2 value for this 4 would be 2. And you can see the values here. Similarly for y lag 3, similarly for y lag 4. So I'll explain what is this y step 2. We have this y step 1 here. So for y step 2, consider this value 0. We have to take the further down the line, whatever the value is. So here the value is 1. So for this record, for the 0 value, the y step 2 is 1. For this one value, the y step 2 is 2. For the second value, the y step 2 is 3. And that is what has been listed here. And similarly to y step 3 also. So for 1, it is 2, 2, it is 3, 3, it's 4. So that's how it has been aligned. So you can see, like how it forms the series. So for, we can consider this record. So for 4, y lag 2 is 2. And for the same 4, y lag 3 is 1. And for the same 4, the y lag 4 is 0. So for this record y, the y step 2 is 5. And the next one would be 6. So I hope you can understand this. And this is very important when it comes to time series project. So there are four important multi-step forecasting strategies. So the first one is multi-output model. The second one is direct strategy. The third one is recursive strategy, and the fourth one is direct strategy. So we'll just get into a little deeper into what these strategies are. So the multiple output strategy. In actually, the diverse realm of forecasting, not every scenario is about predicting a single outcome. So there are situations where we are interested in multiple interconnected predictions. And this is where the multiple output forecasting actually, comes into picture. What it actually does is, like unlike any traditional single target predictions, multiple forecast output forecasting actually involves predicting multiple future values or variables at once. So for example, we can consider, like linear regression and neural networks. They are capable, these algorithms are actually capable of producing multiple output during a single model execution. So this would be, like a sample plot of how a multiple output model would look like. So now we come, like we can go with a direct strategy. So it is actually a granular forecasting approach. So this direct strategy is actually, like in forecasting, is about tailoring the predictions to each specific step in a forecast horizon, ensuring the precision and in adaptability. So you can see in here, it actually uses different models for 1 step ahead and 2 step ahead. So here you can see, if this is 1 step, consider this as 1 step, this is second step, and this is third step. So for 1 step it would use one model, and for the second step it would use the second model, and for the third step it would use the third model. So there are 3 different models engaged in this to produce 3 different outputs, mean 3 different steps. So that's called direct strategy. And okay, so this actually, like this is just a point about how it actually works. And we'll see, like, like why to use the direct strategy. So each step in the horizon may have unique characteristics. So in this direct strategy has the capability to capture these unique strategies, and the errors of one like one of the forecast step wouldn't affect the other. So such independence can be achieved using this direct strategy. And also different, when you use different models, it is much more flexible. And that's how you can capture all the nuances of those minor details of each forecasting. And now we see like the recursive strategy. So this is a single model that is used for there's only one model, and then we are using it for multiple step forecasting, meaning you you forecast one step, you forecast this one step using one model, and then you get some predictions, right? You get some output. So you give this output, loop as a feedback loop again to the same model, and then you get this second step. And once you get this output, you feed to the same model to get this third step. So that's called recursive strategy. So that's what it has been like explained here. And The fourth one is direct strategy. Means this is actually a hybrid approach, meaning it blends the direct and the recursive strategy. So here the individual models are actually trained for each step, but the forecast from the previous steps are fed back as new lagged features. Meaning, so you have got individual models. Say there's first step. For this step, we have a model being trained, and it is used for forecasting for this step. And once we get the output from there, it has been, like, if I'm not wrong, I was trained for, sorry, one second. Okay, got it. So, sorry, there was a small confusion over there. So we have got different models here. So for this step, we are training, like, we use one model for training, and then we are getting the output. And then this output is being fed into there's not second model, and then we get this output as, like the second step. And this output has been fed into the third model to get this output, the third step. So that's called direct strategy. And that's all. When it comes to the slides, we'll dive into the exercise. So we have the store sales, family sales, the test data. Let's see. So here we are, like considering the following 3 forecast tasks. Is it done? Yes. So okay, we'll consider, they have listed 3 forecast tasks here. So 3-step forecast using 4 lakh features with 2-step lead time. If we run this code, so we have got 3 types of data set. We have to match which, like which of these tasks, matches these data set. I would really appreciate, if somebody is coming with the answer. So we'll see 3-step forecast using 4 lakh features and with 2-step lead time. We can see it's not it is a 3-step forecast. No, it's actually 1-step forecast, and 1, 2, 3, 3 lakh features. So can anybody tell me, like, which task does this data set belongs to? So these are the tasks that has been displayed. So yeah, you're right. You're right, guys. Cool. So yes, it belongs to 2. Let us 2. And how about this data set? So we are having 3 steps, 4 lakh values. Right. Right, you're right. Cool. So how about this one? Yeah, that's the remaining one. So we'll check. Yes, it's right. Thank you guys for replying. Good job. So we'll just see, like what the training data and the test data looks like. So this is the date series, and these are the families that we are considering, and this is the sales. So can we identify the forecasting task for the store sales competition here? So meaning they're asking, like, how to like basically identify the forecasting task from this training data and the test data. So we can actually do it by, say we take location, we just take a random one, say 9 for C4. And we can check the shape. Wow. Okay. So it's 16, 2, meaning this is a 16 step forecast, if I'm not wrong. Yes. So it's a 16-step forecast, 1 step lead time, and we can use the lag starting with lag 1. So the one way to find this 16-step forecast is to like consider one of the family, and then like you can see for how much records we want to forecast. Another way is like just consider this, the date starts 16 and it ends in 31, so 31 minus 16, like the dates, it goes to till 16. There should be 16 dates here. So that's how we see what's the forecasting task here. And then we go for like creating the multi-step data for store sales. So y is equal to family sales dot log. All the families have been considered, and only the sales part, not the promotional part. So we are making 4 lakh features here. So make lakhs for y. Lakhs is equal to 4. Guys, always drop the null features. They are causing much more errors. Like when you do the fitting and then the model fitting and the model prediction. So ensure you drop all the NAs at every point. And here we make the multi-step target. Okay, so here we make the multi-step target, means steps is equal to, as I've already mentioned, is 16. And again, we ensure to drop the NA. So yeah. So we have created the lag features, and we have created the multi-step targets too here. And we are just, like aligning it as per as the data that we want it to be. And then here we are doing the label encoder, meaning we are just converting these families, into 0, 1, 2, 3, as we have already seen in the previous exercises. And here we are using the direct strategy to do the forecast, meaning use this regression chain, and we'll use XG boost, XGB regressor model here. Yeah, that's right. And then we'll do the model fitting. It's taking some time. Cool. So, okay. So now we have forecasted for, like 16 steps for this date for this family. So the first step for automotive family on this date, it would be 6.70, and for step 2, it is 6.5. So these are all the forecasted values for this respective families here and it has been forecasted for this particular date. So if we see the plots here and here, so this gray lines are actually the actual values, and this is the beauty forecast. The colored one is the forecast one, and you can see it actually, like to some extent, it actually reflects whatsoever it's in the actual values. So I think this is a decent time series analysis, but when it comes to, like any industrial uses, it should be still more accurate. So that's it, and I'll end my presentation. So thank you so much for listening. So you can come up with any questions if you have.
Thank you so much, Devabria. If you have any question, please drop it in the chat here. It was really good. I learned a lot as well. Okay, so I will start share my screen because we have a little bit of survey, like short one. We need you to fill this out. Yeah, can you stop sharing the Vibria? Thank you. Okay. Okay, so we have this survey. You can scan the QR or like write the link in your browser, and we'll get these responses, and we'll make a raffle price now. And after this, we will have another raffle prize because this is the fourth and last session of the StudyJam. We will have another one for all that attended all the 4 sessions. We will have raffle during next week for one person. He will receive a Google Mini. Also, we will have another one coming.
The screen. Sorry, Chaima, your screen is not.
I'm freeze.
The slides. Yeah, the slides are not advancing. We only see the.
I'm just leaving this so people can take it.
Okay. Okay.
Yeah, I'm moving, but I will show you the rest. So we have three raffle prizes. So take this one first, and we'll let you know about the other ones. In the meantime, if you have any questions, leave it in the chat. Or open your camera and mic and just talk. Yeah. So let me know when you are finished the survey so we can start the raffle. Or anyone has a problem with the link or something, let us know. Everyone is done? Like 1 more minute, start the raffle. We have only 6 people filled it up, so where's the rest? Like, yeah. Is anyone facing challenges to open the link or something? No, you can enter your information, Richard. Yeah, you can win this again. No limit. You can put your information, no worries. Even the speakers, they cannot, I think. I see Debbie, I see like, I don't know. Just test your luck. Okay, should I start, Vanya? We have 6 people. Fill
Sure,
this.
sure, go for it.
Okay. Hey.
Congrats, everyone.
Yeah. So yeah, for this one, just a minute. Okay. I lost my presentation. Just a minute. Okay. Stop sharing for a minute. Okay, we'll share again. Okay, so Vanya will reach out to you again when to give you the price. Also, we have another one coming here for Edmonton residents. If you sign up for this Google I/O Extended and you came like in person, so you will enter also a raffle prize for Chromecast. And the other one, if you attended all the like the sessions for this, you will be entered prize to win home mini, like the 4 sessions we run, the previous 3 and this one. Like we will do this through this week, and we'll let you know by the end of the week. So after you completing all the session, the code sessions in Kaggle, you will get this like similar to this certificate. So please do that and complete your learning path for Kaggle like journey. Also, yeah, like if you have any question or you're confused about something, we have a Discord channel that we all in it, and we have a lot of experts for machine learning. They can answer any question you may have in the future or while you do your training. So we will be happy to answer that. And that's wrap for that. And if you like to volunteer with us, please fill this form. And if we have any future events, we need speakers, we need volunteers, we'll reach out to you and we can collaborate and do more awesome event together. Yeah, and you can here join the Google ML Community Network. They have a lot of resources, help, like all the way in your learning journey. So yeah, also please do join this channel and you will get a lot of information from there. So that's it for today. I hope you enjoyed, and yeah, like we'll meet you the very soon extended. please register if you are in Edmonton, and if you are able to do some vacation in Edmonton, will be great. We'll have you here.
Just before to finish, I need people to RSVP to Google I/O Extended to complete the draw.
Okay.
And also, and also for completing your levels of machine learning StudyJam, send me an email. I will drop in the chat the email with your attached certificates to make the draw. I will share the email. We're going to give 5 minutes so people are SVP. Can you go back to the slide with the
okay. I will do that.
We're going to have like 5 minutes. Sorry. I don't see anyone registered so far. What is happening? You don't want to win a Google Chromecast?
Maybe nobody in Edmonton? Is anybody here in Edmonton? Because it's
Richard. Richard is from Edmonton. I know that for a fact. We cannot hear you, Richard.
Oh, there we go. I had my manual mic on. I can't attend the event. I unfortunately.
Aww.
I would love to, but I have plans. So.
Okay, sounds good. Thanks for that, Richard.
So Manoj, maybe the only one here.
No, there's another one on the raffle as well.
Okay,
so it's going to be a hard one. It's like tossing a coin, basically.
Okay.
Mary, maybe you want to join us for Google I/O Extended. You need to do the drive and carpooling with Shaima.
Yeah, I'm in Calgary now. I wish I can come, but I'm. Yeah, I will not go for this price. So.
Just 1 minute left.
Okay. I will stop sharing, Vania, and you share your screen if you want.
Okay, yeah, I will do that. Just I have thousands of tabs now.
Okay.